I know that. All right, so Eric, what's your question? So I'm gonna, by the way, to do this kind of delivery, I have to be seated. So I've taught for a long time standing up and writing on chalkboards, but it's a sort of different delivery style. You'll have to bear with me because the podium isn't actually equipped to do the kind of things that I want to do for recording and all of that. So I have to kind of bring in this whole setup to do that and annotate the slides. And it asks for a different, like for me to be seated, and so I hope that that's okay with you. Okay, yeah, you bet. So we do, yeah, I mean, you know, if you, maybe you haven't done well on, I want you to succeed. And you know, that you're going to have to be a partake in that. And so I'm recording these things, and all of this material is to help you succeed and pass this class and get the grade that you want. So having said that, Eric, what's your question?
Yeah, so for the quizzes, do we need to be present? And
No, the quizzes, you do not need to be in the classroom, do not need to be present. It is expected that you obey academic integrity rules. All right, so that means that you should not be collaborating with anyone. The work that you do should be your own work. But in having said that, you do have available to you the notes of the class, and you have available to you MATLAB, right? During the quiz. All right. And were I to restrict that in a different way, it would actually put every single person here at a disadvantage if they were to follow that, because I know that some students may not actually follow that, and there's no way to enforce that. So that is the clear and present situation when you assign online quizzes. But it is assumed that you are following the academic integrity code. Not collaborating, I think, is the most significant and overt violation. So if I walk, you know, past the laboratory and I see two students sitting next to each other taking the quiz, very possible, that's going to be a problem. You can't actually be right next to each other, looking at each other's screens, you know, like collaborating on a quiz. I warn you. I'm a faculty member that serves on the Honor Council. I believe strongly in academic integrity. And I will not hesitate to act if I see it being violated. I just want to let you know that, so that you can make your decisions in knowing that. You know, so like, and another thing about this whole thing about how to do quizzes, like this, the way that we're doing quizzes is actually consistent with how we'll do the midterm, but we will actually be in class for the midterm. And I will take attendance. I will be like, okay, you know, and I'll make sure that every person that's taking that midterm is in this room, taking that midterm here in this classroom. But you will have all the notes available to you. You will have MATLAB available to you. I'm going to bring in some extension cords so that you can plug your laptop in, especially for the final, where you really have a long period of time with potentially no source of power. And the one difference between quizzes and the midterm and final is that you have the opportunity to capture the last question of those examinations is an opportunity to capture all of your written work and submit that. So that will accompany your submitted work, you know, in terms of all these numbers and things that you type in. If you mistype something and you submit work that's correct on paper, you will get credit for that question. If you submit something that's nearly correct on paper, but say you did a miscalculation, or maybe you made some kind of a small error along the way, the purpose of the submitted work, in addition to the examination on Canvas, is to assign partial credit. And so that will be reviewed and partial credit will be assigned. And often grades, you know, can change due to that partial credit, you know, as long as what you're doing there on the paper reflects knowledge of the material as it relates to answering that problem in the class material that you're asked to learn here. So that's kind of that's way bigger an answer than you needed, but that's sort of, it's an opportunity to kind of, you know, like kind of set expectations and like how is this all going to work, right? And that's what I want to tell you.
All right, so we can use notes and we can use now like the quizzes and we don't use them.
Correct. Yeah. And you also must obey the law, the rule of academic integrity.
Right. If you have your notes and that, then I don't think
Yeah, the idea is that if you work on the homework and you're kind of reviewing the lecture notes and you're reading through the textbook and doing the reading assignments and kind of brushing up on the materials, then these things should all, should be well prepared for these quizzes. They are challenging. My classes are challenging. Okay, my classes are challenging. You will be challenged. Typically, and let me, I don't know if this, everyone's had this discussion. So my grading is typically my classes scale to have about one grade level lower than you might be accustomed to. And the way that that's compensated for is that I basically add a shift, a constant number to every single person's grade in the class at the end of the semester. And the shift could be 8 points, it could be 10 points, could be 20 points, could be 100 points. It could be, typically in the past, it's been around 10 points, but the shift is my decision. It's a decision that I make, and I essentially set the top performing. My process for that is I take the top performing student in the class and I say, I've taught this class for 17 years. This student either should be set to 105. They're like fantastic, like incredible, right? They're going to go on and be the next Elon Musk, maybe the 110, whatever. I set them to a number that reflects their performance in terms of the expectation level that I have for a student in this class. And that number could be over 100, could be 100, could be less than 100. That's never happened, but it can be anything. As I've done this grading scale method for not 17 years, but around 15. And typically a shift is around 10. All right. That's not a commitment for it to be 10, nor 11, nor 9, nor 8, nor 12. That's your information that I can give you about the grading mechanism that I use. Is that clear to everyone? Yeah. All right. Any questions at all on any of that stuff? It's good to, it's kind of like, since we're here in person, you can maybe revisit any of those questions. Is there, so if there's questions on the quiz, that's a kind of, yeah, you have a question?
Is it possible to, once quizzes have been like completely done, release
Yeah, oh, that's a very good, so the practice is just to release the answers. Usually I do it the day after, because sometimes students that have disabilities or other circumstances have this period of time after the quiz because there may have been incidents or whatnot. So I usually release it the day after. Let's go and double check that to make sure that they are available to you. So it kind of makes me question whether or not this has been done. Your question, I'll get to you in just a moment, but so show correct answers for the homework is there, right? So you guys can see the correct answers for the homework, right? And it's there for a week, right? Right. So it's there for a week. That means it's there for a week. What happens after a week? It's gone. I want you to know this. You're completely within your right to download it as a PDF and procure it. All right. But it's not something that I'm going to make available during the midterm for people to just click on and look up. Okay. And it's there for you for a week, right? So, if you want to keep it on hand, procure it, download it. Okay. And it can be yours. All right. But it's only there for a week. Okay. I wanted that to be clear. And if you don't download it, your colleagues might download it, or you what I mean? Like, so those answers should be out there somewhere available to you. And if they're for some reason, they're not available to you, come and talk to me and we'll figure something out. Okay. But realize that everyone kind of gets a different set of questions in a lot of circumstances. And so the questions and the answers that you see in some cases may be very specific to your exact quiz experience. And so has that happened for the quizzes so far? Is there? So I will double check to make sure those answers are available. And they are available for a week. So download them and procure them if you wish to hold on to them, because they are available for a week, and the rationale behind why they're available for a week. So there's a question in the back. Yeah.
The only way you can help our grade is to shift the use of the weight dropping or
So is there something that you expect me to do to help your grade?
No, that's, just want to make sure. So that's,
No, you'll be graded according to the syllabus, and I promise to do that. And any professor that doesn't grade according to the syllabus should actually be taken up with academic affairs. Yeah, so that's exactly how I'll grade. You got a question? Yeah. So the solutions are are available with the correct answers of the quiz. But you can always come and if you want more detail, right? Then that would be something that you would come to like office hours and kind of like say, okay, I capture that stuff. And then what I'm asking for to happen in office hours is like solutions that get written out, we just kind of post those things too. But I haven't figured out a mechanism to like make them not permanently posted. So that hasn't happened quite yet. But that's something that I'd like. So I'm trying to figure out the solution to that, which is yet another problem. But anything that gets worked out from office hours, I'd like to share with you as well. Like if things get written out in much more detail, kind of justifying things. So yeah, that's the. Does that answer your question? Okay. Anything else? Okay. Then we will dive into lecture. And so during the quiz, I posted homework 3, which will be due Monday night. And that presumes a certain level of progress in terms of lecture. Of course, if we don't make that progress, it'll be moved to Wednesday night, and we'll have the quiz on Thursday instead of Monday night and Tuesday. It's all contingent on making progress. And with that, I think we'll just dive in. So we're in lecture 5. We finished lecture 4 last week. And lecture 5 talks about this sample domain representation. And so sample domain, we're talking about the sample index, which is n. And when we're talking about sample domain, we're thinking of functions of the sample index. So we're thinking of functions x of n, y of n. We represent a system in the sample domain mathematically as y of n is some kind of operation that the system does on x of n. So t would be that operation, whether it be exponentiation, squaring the n index or whatever. It can do all sorts of interesting things. And the things that the system does might make it time invariant to ti, or it might make it linear or not have those properties. But something that has both the linear L and the time invariant property ti is termed an LTI system. And in this course, we really focus on the analysis of LTI systems. Why is that? Well, LTI systems form an important part of our world. Many things are approximately linear. For example, acoustic energy. If I shout into the room, it creates a certain amplitude or volume for everyone. If everyone else shouts into the room, what happens to those signals? Do they all superimpose and add? That's an additive system. If I were to shout louder, would you hear it louder? Does it obey additivity? Does it obey scaling? Is that kind of model additive or linear? Yes. So just like a lot of physical processes, such as acoustic energy, lights, turn on the light, you get a certain amount of illumination. Turn on another light. Do you get more illumination? Yes. Is it additive? Yes, generally additive. A good model for light is additive energy for illumination. If you make the light brighter, does the illumination get brighter? Does it scale? Yes. So a lot of physical processes, circuits, they can be modeled well as linear systems, linear time invariant systems. So that's why we restrict our attention really to linear time invariant systems, because these systems are both important in practice, and we have very strong in classical theory that tells us how to predict these systems and in fact design these systems. So we'll talk about that. We'll talk about what is happening here. Okay, so my cursor is apparently missing. I don't know how life is going to go on like this. Wasn't it here a moment ago? Yeah, I see it here. Fascinating. All right, well, we're just gonna try and survive this way. I might have a look to jot down a little bit more to just find out where I am, but we just go on. All right, these are the sections from the textbook, section 2.3, which is right here. And section 2.4, which I guess I'll box right there. And these are talks about discrete time convolution and properties of LTI systems. So we're talking about representations for LTI systems. Representations for LTI systems. And there are 4 ways to represent an LTI system, and I list them here. There's the impulse response, which is the focus of our chat today, a difference equation, we'll chat about that in another lecture, and yet another lecture we'll talk about the frequency response. And a totally separate chapter is dedicated to the Z transform to representation. So we're talking about the impulse response. So the impulse response is a way of representing a system. And again, what is a system? So we have this representation for a system, looks like this. And so the system itself is this thing here, and the impulse response represents that system as H of n. Okay. And so again, we have this, it can be represented 2 different ways. This block diagram is one, and then as a general mathematical operator is another. So it's a mathematical equation, it's the top representation, and the block diagram, the bottom representation. So let's look at these linear time invariant systems. Let's see if I can just. Yeah. Oh, looks like it's just not going to work. So we have this, what have we done here? We've decided to input a specific function. That's the delta function. When does this delta function occur? What sample index? When n is equal to k. So it's a delta function when n is equal to k, and then we input that to the system and we look at what comes out, hk of n. That is the de facto definition of the impulse response. Why is that a meaningful definition? So this is a very important, so this definition of impulse response is a very important concept. If you're ever trying to figure out what a system does to understand the system itself, you can input an impulse to the system, and what comes out is the actual linear time invariant representation of the system itself. Remember, h of n is supposed to be the system. So if you were able to input an impulse response to the system, the h of n, the impulse response, comes out. It's the response that the system has to an input when that input is the delta function. What do we call the delta function? We call the delta function the impulse function, right? It's another name for it. So the impulse response is literally the response the system has to value that the system outputs when the input is an impulse function. I'll tell you an interesting example, probably heard it before if you hadn't, of how to use the impulse response in ways that you might not think about. Like, this is an incredibly important result, or just concept. When I finished my graduate school, I was very interested in acoustics and music. I got an engineering job, and after I got my first paycheck, I bought myself the most expensive stereo system I could buy, which was a Bose Lifestyle 12 system. It was fantastic, still have it, wonderful. And I played something on it, and my understanding from acoustics theory is that the perfect representation for music is a representation that restores the exact frequencies or the music content as it was played. So the microphone transduced the recorded music, it goes on to disk. And then when you play it back out, it's supposed to sound exactly the way it was recorded, because that's what people that made the music sort of intended for you to hear. So it didn't sound like what it sounded like before when I played it through my other stereo system. So I asked the fundamental question is like, is the stereo system itself doing something to this music? Does it have what they call a flat response? A flat response means that the music being played out of the system is exactly an exact replication of the music as it was recorded, right? That means that all frequencies are reproduced at the same magnitude as they were when they were recorded. And that means that the system, the actual stereo amplifier as a system has a flat. In other words, it reproduces all frequencies at equal amplitude. It multiplies them by some constant A. That means that if the frequency was very small, like when you're as a non-amplified signal, it all amplifies all frequencies in the same way. So what did I do? I did something analogous to the delta function. I sent a delta function into my loudspeaker system, and I checked to see if it reproduced if it was a flat response. There is it should be a sync function, right? If you have a box in the frequency domain, you should get a sync function in the time domain. It was not at all a sync function, and so I said to myself, well, maybe I got a bad stereo. And so I wrote up all of my results and analysis and I sent it to Bose. And I said, well, what's going on here? This is what I find my speakers doing. Why isn't this supposed to be, a really wonderful speaker system? And so about 4 weeks later, I got notes back from, so in legal form, from Bose saying you cannot reverse engineer our loudspeaker system. This is Bose intellectual property. So it tells you how simple it is from a engineering context to threaten the intellectual property of huge companies, because you just simply use the fundamentals of the theory that you're learning here. And in this case, I reverse engineered, well, what is the Bose lifetime experience inadvertently, which is essentially how they manipulate the frequency content of signals so that they are perceived to sound better than other loudspeaker systems. And that's fine. I didn't realize I was doing that. But that just tells you how trivial this trivial concept of an impulse response actually can be leveraged to reverse engineer anything. Yes. So what would an impulse sound like in a loudspeaker system? That's what it'd be. It would be like now you really don't want to do that. So I didn't actually do that. What I did is an analogous thing called a chirp Z transform. So it just sends all frequencies through at equal amplitude and it sounds like a frequency sweep. So it goes, and you'll actually play with one of these. We do a frequency sweep for understanding filtering, where we eliminate parts of the audio spectrum and it kind of goes, and it stops and wherever your filter cuts off. And so we do that as part of one of our filtering experiments. We do some audio filtering so you can actually hear the filter doing its work. And so I did something analogous to the delta function because there is because I had paid so much money I did not want to send an impulse into that system. So there are analogous techniques to do something that's mathematically equivalent, but doesn't damage your system. Because remember, an impulse response has infinite energy and infinitesimal time. So ultimately it would be kind of unbounded physically and it would overdrive all of your, it would do bad things for anyone that values their acoustic equipment. And so there are alternatives that are actually bounded and that still allow you to interrogate the system. Any other questions? Okay, so that's the idea of the impulse. The impulse response is what comes out when you put in the delta function, and it's how we represent the system. So we call it H of n. So Therefore, we can actually represent the input using unit impulse sequence. So we actually do it, take x of k, multiply it by delta function at that time, and do a sum over all of the delta functions. And it's just like adding a bunch of single values for x at every index k. This is equivalent to writing down x of n, but the reason that we write it in this way is to get used to this infinite summing notation. We're going to see that because that comes up in convolution. And what we're doing is we're summing over an index k. That's part of, that's at the bottom of the summation, goes from minus infinity to infinity. And we're actually taking x at the index k and multiplying it by delta of n minus k. Of course, delta of n minus k takes on the value 1 when n is equal to k. So essentially, we're taking every value of x and multiplying it by 1. So it's just a mathematical way of writing it down. And it's basically how you might write down x if you were to write it down as a sequence of delta functions. And so that's what this equation means. Kind of have to find myself. So we look at the linearity property and we basically plug this in as a system. So there's a system of our function x of n, and that allows us to actually look at the system as it operates on a bunch of delta functions. And we already know that the system, when applied to a delta function at n minus k, is in fact the impulse response here. I apologize for the mess. It's hard to know where I am on the slide when I'm, oh, what's going on? I sort of saw a cursor for a second. I'm just going to ignore it. Yeah, that'll be a technical hurdle to overcome. Did not experience that hurdle last semester, so I don't know. This is a time varying system. You sit down one day and it gives you a different response than it does the next. All right, so convolution as an LTI system. You can represent any linear and time invariant system through convolution. Why is that? So convolution is actually a representation for a linear and time invariant system. There are 3 ingredients to the convolution equation. One ingredient is y of n. The next ingredient is x of n. And the third ingredient is h of n. So when we write down the convolution equation, we have to have 3 functions. First function is, in this case, we write it down as x of k. All right, this function is static. It's basically a function of k alone. H of n minus k is actually shifting. It's a function of n and k. And then we sum over all indices k. Now, when we sum over any variable, think of it as like integration. So if I integrate over a variable x dx from a to b, what do I get? A function of x out?
Yes.
Easy now. It's a definite integral. It has an upper and lower. This would be x squared over 2, right? Evaluated x equal to a, x equal to b, right? Now, the answer to the same thing again. Is this going to be a function of x when I evaluate this? It's going to be a function of a and b. It's going to be a function of the endpoints. Think of this summation in the same exact way. It's a definite integral, but the endpoints are sort of indefinite. They're minus infinity, infinity, but the function that comes out is y of n. It is not a function of k. Right? The variable k is gone. When we sum over a variable, it's you think about probability theory, we call it marginalizing over that variable. That variable is no longer going to be part of the equation. Yes.
Would you say that in a simplification that n and k would be a and b?
I would think of this summation as the equivalent of the integral, and in the lower and upper bounds is minus infinity, infinity as sort of. So think of summation as discrete version of integration. So when I write this thing, I might write k equals a to b of x of k. And that would be like kind of the analog of the continuous interval. Yeah, a very good question. Because it's not exact. I didn't really clarify that. So what does filtering do? So h of n, we call h of n the filter, right? So what do filters generally do? Well, I don't know. I'm a coffee drinker. I hope none of you are. It's a terrible habit to have. But when I think of filters, I think pragmatically, maybe a coffee filter. What does it do? It separates, it keeps separate the water from the coffee grinds so that I don't drink coffee grinds. And so when I pass water through it, the water isn't changed in some way. But the filter functions in a way as to prevent some things from passing, but also allowing other things to pass. And so the filter, this mathematical entity, the impulse response, is also a filter, but it works on numbers, and it works to allow numbers to go through certain kinds of numbers, certain for certain representations for these numbers or sequences of numbers to pass through, and it attenuates or makes smaller or rejects, multiplies these other pieces of information by zero. Now, I say pieces of information, but I want to say frequencies. So when we think of putting frequency, we'll do a Fourier transform, and we'll think about these systems in the frequency domain shortly. I want you to think of the filter as a time or a sample domain representation of a filter that operates on frequencies. So it operates on specific sequences of numbers that are the frequencies. And it will allow some frequencies to pass through, and it will reject other frequencies. Right now, if those frequencies that it passes through are lower frequencies, but it rejects higher frequencies, it's called a low pass filter because it rejects frequencies, that are high, and it allows low frequencies to pass through. So low pass, high reject. Conversely, if it allows high frequencies to pass through and low frequencies are rejected, it's called a high pass filter. Now, if it's selective and chooses a small range of frequencies to pass through and rejects everything else, it's called a band pass filter because it will pass a specific frequency band and reject other frequencies. Now, and the other one would be a band reject. It would pass all frequencies except for a collection of frequencies that it seeks to reject. Now, when you're thinking about this, continuing this analog that this analogy that I have with music, has anyone ever had a frequency adjustment to any of their music that they listen to? Now, what are the three primary frequency adjustments that you can make to your music? Low, bass, low, mid-range. It's always called mid-range, but and then high or sort of the tweeters, what have you. These correspond to frequency ranges. And each one of these frequency modifications, each one of these knobs you use to control your music either attenuates if you turn it to the left, so to speak, or amplifies that frequency range and is a filter unto itself. In fact, each one of them is a filter. And the cumulative response of all those filters is the sum of the three filters, because filters are linear in time invariant. So if you have three such filters, and you put them together, you can create an arbitrary mix of the frequency content of your signal as it goes in. And that's in fact what exactly happens when you do that. So so it filters. And so there are two different kinds of actual impulse response representations. There's the finite impulse response, or FIR, and that's all that means is that h of n has a finite number of values. If h of n is finite in length, then it's an FIR filter, a finite impulse response. The impulse response has a finite number of values, it's FIR. The converse to that is IIR, infinite impulse response. That means that the impulse response can be infinite in length. So if I write an impulse response, h of n is equal to u of n, is that an IIR or an FIR filter? If h of n is equal to u of n, the step function, is that a finite impulse response or infinite impulse response filter? Infinite, it goes on forever. It has values that stretch from 0 all the way to positive infinity. So it is an IIR filter. If I write h of n is equal to delta of n, FIR or IIR? It's FIR, it has one value, that's a finite number. It's just counting the number of values it has and asking yourself if the count of values is either some number or infinity. Okay, so another thing we need to be aware of is the sifting property. If we take x of n and we convolve it with a delta function, that results in a shift of the function, x of n minus n naught. So here the delta function occurs at n naught. And the function is shifted so that wherever it was had the value 0, that value now occurs at the index n naught instead of at 0. That's what this function, this equation means. So here's an example of how one might specify an FIR filter. We specify it several different ways. In this way, we just give a list of numbers, -2, 1, 2, 3, 1, and we tell the index at which these numbers occur. So -2 occurs at the index -1. 1 occurs at the index 0, and so forth until we get to index 3, and that's where the value 1, occurs. And so that is one representation for an impulse. So if I write down an impulse response, you will need to be able to look at this representation and interpret it. That's one representation. The other representation we've practiced. It's just writing it down as a sum of delta functions. So in this case, this representation for the impulse response is a mathematical equation. That mathematical equation is exactly the same representation as I have on the previous line. This line here, and this line here are two different ways of writing the same impulse response. So you just need to be aware that, like you be able to cope with both of these formats. One of them might be better if you're trying to do some kind of mathematical exercise. The other one might be better if you're trying to graph it or something, but you don't know what you'll get. Be able to recognize and use both. An IIR filter, here's an IIR filter here. Here's a step function. And of course we have some kind of complex exponential there. That's IIR, goes on forever. Okay, so what is h of n minus k? It's like this, we have this equation and it was a sum, it had x of k and it had h of n minus k in it. And this is a graphical representation. So the convolution equation has k goes from minus infinity to infinity. Sorry for the mess, I kind of don't know where I'm writing. And so the question here is like, what is h of n minus k? Well, we consider, here's h of k. We consider first the function as a function of k, because that's what we're summing over, right? We're summing over k, so the axis consideration is k. And so then we consider h of minus k. So this is this here is time reversal. And so that means that we're flipping the function around the 0 point. Anything on the positive axis flips to the negative, and everything on the negative axis flips to the positive. That's h of minus k, which is halfway there. Then we advance it by n. We add n, right? So you can think of this as h of minus k plus n instead of n minus k, right? And that's the way that this is getting plotted. We first do the time reversal, and then we do an advance. So this is the advance. And that gives us h of n minus k as a function that's been advanced by n after being time reversed. Now note that we're looking at it in terms of the k axis. So it's not, the horizontal axis is k, and n is modifying k, not vice versa. All right, so sifting property. You've seen this before. Yeah, well, wonder if my hand is creating a problem. So sifting property is a situation where you just plug in the delta function for the impulse response. And when you plug in the delta function, some simplifications occur. You get this. So here we're plugging in the delta function for h of k times x of n minus k. And we look at this infinite sum. Now, one of the two terms here is a delta function. It's delta of k. Where is delta of k going to be non-zero? When k is equal to 0, right? Delta of k evaluates to 1 when k, its argument, right? Not n, in this case it's k, where k is equal to 0. Well, so that means that we can plug in just k equal to 0 to our sum. There's only one term in this infinite sum. Every other term is 0. And so when we plug in k equal to 0, we get the delta of 0 times x of n minus 0, and of course that's x of n. So when you take h of n equal to the delta function means that the system's a delta function, and now the input is arbitrary. We get the dual relationship. X of n comes out, right? So before we talked about the delta function going in and h of n coming out, but if h of n is the delta function and x of n goes in, x of n comes out. Right, and so it's sort of the duality of this thing. I think that's all that we really need to analyze. But if I were to do this a little bit differently, say I were to do x of k delta of n minus k plus 1, I guess what would be the answer to that convolution problem?
It'll be, xk plus 1. Right?
So, what was it? So we want to ask the question, where does delta of n minus k plus 1 equal 1? How do we solve for that? We ask the question, when is n minus k plus 1 equal to 0, right? Like if we just always have programmed in this approach, you cannot go wrong if you programmed in the approach. What's inside the brackets? Set it equal to 0. Solve for the thing that you're solving for. In this case, we're solving for k, right? So then we just take this equation, n minus k plus 1, and we solve it for k. Well, we see that k, when k is equal to, when k is equal to n plus 1, this occurs, right? And so if we keep applying that, like remember and apply, we can find out what term is going to be non-zero when k is n plus 1. Then we plug that in for k because it's the only non-zero, right? So then the result is going to be, where if I can write it, it'll be x, k is equal to n plus 1, x of n plus 1, delta of n minus the term n plus 1, right, plus 1. We know that's going to come out to 0 because we just solved for that. So this term in here is equal to 0, and we get x of n plus 1 coming out, right? Because delta of 0 is 1. So we get x of n plus 1 times the number 1, which is why the delta just disappears, because delta evaluated at 0 is equal to 1, right? So again, I'm trying to kind of champion this, this process of thinking about where these functions are going to occur to allow you to address these mathematical questions, because it might not be immediately obvious that that's the answer when you look at that problem, right? You have to kind of go and apply the fundamental principles of the analysis there. Okay, so sifting property of the delta function, again, analyzed, and now I kind of do this again. I kind of make it a little bit more general, right? Before I made it, I was like, what, -1. I did n minus k plus 1, right? Now I'm just doing it for a general I. And we find that, n minus k minus I is going to be equal to 1 when I is equal to n minus k. Now this is a sum. I'm changing the sum as well. So I'm doing the sum over I now. And I'm pointing out here that you have to look at what the sum is over and solve for the variable in the sum, right? In this case, I'm solving for I because the sum is over I, right? So there's more to the story than just saying, okay, choose a variable and solve for it. You will not get the right answer unless you choose the right variable. That is the variable that's changing during the convolution sum, which is the variable over which the summation is being taken. Okay, that's the critical piece of information here. Of course, we get the same exact result. In this case, the sum is over I, so the result can't have an I in it. We know that it has to have an n and a k in it, right? So these principles that I'm kind of remind you of what should be in the result and how to approach the problem to get that result. That's kind of the keys to success.
Will we ever have like an argument inside of the x function where
Yeah.
it might not be that simple as what we have right now, where xi? Have like I.
Well, typically speaking, so let me write down the convolution equation itself is written in two different forms. There's the X stationary form where X is just at K, and the impulse function, the impulse response shifts with K. And the other form of the convolution function has them switch roles because convolution is distributive. You can do X of convolved with H is equal to H convolved with H. With X. It means you can swap their roles in the equation. So I can write H of, I don't know how I'm going to find my way back here. Okay, H of K and X of N minus K, right? And so those two convolution problems have the same exact output, right? And we'll talk about that. But if you input H to a system having the value X of N, you'll get an output Y, and that output will be the same as if you took X and input it to the system having the value H. And so, yeah, got a question.
So there's no difference in how we solve those two questions.
There is a difference in how you solve them. For sure, there's a difference. Because, and what my suggestion is that you basically make the whatever function is complex or like is more sophisticated in form, you make stationary. Right? It's the thing that you don't have to analyze. Whenever you have a delta function or a step function, you make that the thing that shifts, because that we have prescribed ways of solving. And so we'll go through, when we talk about convolution, we'll go through all four variants of possible convolution problems in the discrete domain and the way to solve every one of those four. Right? There's two kinds of, just a second, there's two kinds of impulse responses: finite impulse response and infinite impulse response. And there are two functions in the convolution equation. So you can have X as finite impulse response, H is finite, and then you get one approach for solution. You can get the situation where X is infinite, H is finite. There's a solution method for that. That same solution method also applies to when H is finite and X is infinite. I'm not sure if I juxtaposed to the order, but if one of them is infinite and the other is not, there's a solution method for that. And because it doesn't matter which one you consider X and H, the solution approach for both of these contexts is the same. Finally, there's a case where they're both infinite. And when they're both infinite, there's yet another approach that you take. Now, the approaches when you have infinite signals will involve using power sums, series, knowledge of geometric series, and this fundamental equation that we always have usually comes up, the sum of a to the n over the values of n from 0 to infinity, which we know if a has a magnitude less than 1 comes out to 1 over 1 minus a. We have that as a homework assignment. That comes up in so many times, it's hard to stress how important that result is. So now you have another question.
I'm sorry, I just want to clarify what you meant by stationary.
So stationary is the first argument here. This guy is not shifting with K. And this guy is shifting with other values of K. So the first part is a stationary part. So, and we'll do some convolution problems. We'll start off with finite first, and there's a method that I suggest there. And then if you look at the slides, you want to get ahead and look at all the different solution methods and how to address them, you can certainly go ahead because all the materials are available to you. But we'll go through one at a time. One at a time. Yeah. Okay, so finite impulse response. Okay, so this is a finite impulse response system. Most common form is that we have some finite sum here because, well, it's a finite impulse response. Let's assume that our impulse response has capital N values. Well, starting at 0, that would go, those capital N values, if they were all in order, if they all occurred at sequential indices, we could summarize them as a sum from 0 to capital N minus 1. So say we had 2 values, right, for H of N. Be a sum from 0 to 1, which is 2 different values, right? So that's what this is a representation for a finite length impulse response. And we can write out the terms of this. How many terms are there in this summation? How many non-zero terms more specifically? Yeah, there are capital N values that are non-zero, and it's a multiplication that's occurring here. So that's their capital N result values in the sum. And if we write out all of them, which I'm converging, okay, so that's 1 2, so forth and so on, all the way out to this term, and I don't know why X looks strange there, but this is capital N terms. Right? And that's writing out every one of the terms in this summation where I plug in the value of K for each one of them. And so here's an example of a finite system that where the value of H is the thing that's multiplying the delayed values of X. So it's a coefficient that's multiplying the delayed values of X. So here we have the coefficient H of 0 multiplies X of N. H of 1 multiplies X of N minus 1. So when we see an input-output relationship, X, Y as a function of X's, we actually can just pick out the terms of H of N. In this particular case, H of 0 is going to be the number that multiplies X of N. H of 1 is going to be the number that multiplies X of N minus 1. And that's all that I'm pointing out here, is that H of 0 and H of 1 are 1/2, and all of the other terms of H are 0. Infinite impulse response. So I guess as you can see, I'm immediately recommending techniques for solution is to consider the geometric series, right, that we talked about, the sum alpha to the n from 0 to infinity, and that's equal to 1 over 1 minus alpha if the magnitude of alpha is less than 1. If it's not less than 1, the sum is infinite. And can a convolution be infinite? Yes, if the system is unstable, you certainly plan on it being, it could very well be infinite. So you could have this sum come out to infinity. So when we're dealing with IR systems, we're going to have to use our knowledge of geometric series in order to calculate the output. So there's other different, I mentioned other things that we actually are going to discuss in later lectures. Other ways to get the solution is to use a difference equation and calculate the solution to the difference equation, or take the Fourier transform of the system, Fourier transform of the function, multiply them in the frequency domain, take the inverse Fourier transform, and get the solution that way. So this is kind of reminding you of these properties from 3111, and that these properties are, again, going to be the things that we talk about in this class. It's not what we're teaching right now, it's not, but it will be. These are other ways to solve convolution problems, right? We have all these different representations: impulse response, difference equation, and the spectral of Fourier transform, right? You can solve using any one of those 3 representations. Right now, we're talking about how to solve it if you're using H of N, the sample domain representation, which is the subject of the lecture, sample domain representations for LTI systems. There's also difference equation representations of LTI systems. That's our next lecture. Then there's the Fourier transform representation of an LTI system. That's the lecture after that. This is a 3-lecture series. And we understand these 3 things, and we understand how they all relate to each other. And using that, you then take your midterm. And that's sort of the scope of class, and we're beyond the scope of this lecture, which is, so it's 2:15. We'll have to stop here. We'll continue, pick up here, and we'll actually very shortly be talking about how to actually calculate convolutions. We'll talk about these couple of systems here, and then do discrete convolution. So I'm going to stop. Did I even start the recording? I did start the recording. Thank God for that.